Yeah, good evening all. You can mark your attendance. Google link is posted on your class group. Please mark your attendance. So meanwhile, today we'll be discussing the frequency response of the Morse cascode. So in the earlier class, we have discussed the small signal analysis where we derived some equations for the gain, isn't it? And the thing is, the conclusion is that you could increase your gain by a factor of A naught. Okay. So the overall gain is Gm into R0 the whole square, which is shown as per this particular equation. And it is being also shown that whenever your load resistance RL is equal to A0 into R0, okay, you know that always your gain varies with your load. So if you can set the load resistance equal to A0 into R0, then you will be able to achieve your gain approximately equal to, see, minus A naught square by 2, which is very much large. But for the second case, we have proved that whenever you are taking RL equal to R0, which is quite small, then your gain will be just minus A0, which is equivalent to the gain of a typical common source amplifier. Okay, so this much particular gain you can achieve by using a CS amplifier. So you don't require a cascading configuration for that. Okay, our intention for cascade configuration is to increase the gain. So you can get an increased gain only if the load resistance R equal to A0 times of R0. So you should be able to design this particular load resistance whose value is A0 into R0 so that you get a gain approximately equal to minus A naught square by 2, which is very much enhanced. Okay, so this only keeps a validation of your cascade amplifier. So the merit of the cascade amplifier can be explored only if you are able to take the load resistance value equal to A0 into R0. Understood? So that we have shown in the previous class. So in the small signal analysis, we have derived the equation for input impedance, input resistance followed by the open circuit voltage gain, overall voltage gain, and how this gain is getting varied with respect to load resistance RL. That also we have seen. Now today we'll be discussing about the frequency response of this cascade amplifier. You know what is frequency response means, isn't it? What do you mean by frequency response? Frequency response is the plot of gain versus frequency, isn't it? That is how the gain of the amplifier is getting varied with respect to frequency. So you should be able to give a proper input frequency so that based upon that frequency you will get the gain at the output. Okay, that is if you are increasing the frequency to a larger value means your gain will decrease. So normally you have to find a cutoff frequency FH. So what is the speciality of the cutoff frequency FH? That is beyond this cutoff frequency your gain will decrease further below to 70.7 percentage of maximum or 3 dB value, isn't it? 3 dB is nothing but 70.7 percentage of maximum gain. So that much gain is okay, it is acceptable, but still we are increasing the frequency means what will happen? The gain will further decrease beyond or below the 70.7 of maximum. Okay, so that is not at all acceptable for a load. The load will not work with this particular gain. So you have to operate this amplifier with respect to a particular frequency that comes in between 0 and fh. Okay, you should be very careful while giving your input frequency. Your input frequency should lie between 0 and fh. That is nothing but your bandwidth of an amplifier. You know what is bandwidth? Bandwidth is a range of frequencies through which your amplifier will work properly. Means you have an appreciable gain at the output. Okay, if still you are increasing the frequency beyond fh means your gain will not be acceptable. It will decrease below the 0.707 amax or 3 dB gain. So that is what we are trying to derive from this frequency response portion. So this is very important question in this particular module, that is derive the cutoff frequency equation for a cascade amplifier. So see this figure. So you know what is cascade configuration. Cascade is a combination of two different configurations simultaneously implemented. So in the first stage you have a common source as shown in this particular diagram. So this is common source and this is common gate. See, I've taken gate at the ground. So gate is common to both the input and output. Input is the emitter. To the emitter, I have connected the output of the first stage. To the emitter, I have connected the output of the first stage. Output of the first stage is nothing but the drain. Okay. So the drain has been connected to emitter of the second stage so that it is now become a cascode configuration. So cascode is a combination of common source and common gate together connected. And apart from these two transistors, here I have shown a signal resistance R6. Then all the junction and junction capacitance or internal capacitances and the load capacitances as well. See, there are 5 capacitors included in this particular diagram. So based upon this 5 capacitors, we are trying to find the time constants. Okay, you know the procedure of finding the cutoff frequencies. That is in the previous module you must have done. That is, while calculating the cutoff frequency, what you have to do is you will have to find the individual time constants. Okay, time constant is nothing but the product of resistance and capacitance. So if you can find the individual time constants, next thing what you will do is you will add all these time constants together to get the total value of tau. Okay, so 1 by 2 pi into that particular tau is your cutoff frequency fh. I repeat again, to find the cutoff frequency, what you have to do is you will have to find the individual time constants. Time constants is nothing but the product of resistance and capacitance. So you know, see in this figure we have shown 5 distinct capacitors, not even 5, I think 6 capacitance are there. So individually you have to take individual capacitance one by one. Looking through that capacitance, you will find one resistance. So that resistance multiplied by the capacitance is nothing but your time constant. Understood? Understood the procedure? What you have to do is, out of the total available capacitors in this particular diagram, you will have to choose each and every capacitance one by one, open that particular capacitance and look through those terminal. You will find a resistance R, multiply that R and corresponding C, that is your time constant. Now add all these time constants together, that will be your tau h, that is total time constant. So once you get the total time constant, by simply substituting the equation 1 by 2 pi tau h, you will get the cutoff frequency fh. Now, understood the types of capacitors what I have shown here. First is CL. CL is a load capacitor. Okay, that is nothing but a type of load. So you can't say that always your load is perfectly a resistive load. You might be using a fan as a load, isn't it? You may be using a motor as your load. You may be using AC, refrigerator, etc. as your load. So depending upon the type of load, it can be resistive, it can be capacitive, it can be inductive. If it is a fan, it is an inductive load. Okay, motor is also an inductive load. Fan, it also has a capacitive effect also, because there is a capacitor inside that. Okay, so similarly, depending upon the variations of the load, it will show different features like resistive, capacitive, inductive, etc. So I assume that my load has a capacitive nature, which is denoted by CL. Understood? So in this diagram, we are going to calculate the frequency response. So for that, I have to mention 5, 6 different capacitors. So one by one, I will be looking into it. So one is CL. CL is nothing but the load capacitor which is connected parallel across RL. Now, along with CL, you will have CGD. What is CGD? CGD is a capacitance connected between gate and drain. Identify this is your drain, this is your gate. So actually these are the junction capacitance which is inside this particular device. It is not physical one. Only CL can be considered as a physical capacitance. So can you consider CGD as a physical capacitance? The user is not connecting it, isn't it? It is something which is internal to the device, which is present in between the two terminals. So that is considered as a junction capacitance CGD. Similarly, you will have CGS2, means the second Q2. With regard to transistor Q2, you are having a capacitance connected between gate and source of Q2, which is represented by CGS2. Understood? Similarly, when you go for Q1, again you will have CGD1 and CGS1. CGD1 is between the gate and drain of Q1. CGS1 is between the gate and source of transistor Q1. As it is observed that this source of Q1 is directly grounded, instead of connecting this capacitor to the source, we can connect this capacitor to ground as well, because source is at ground, isn't it? So connecting this capacitor between gate and source is equivalent to connecting it between gate and ground, because source is at ground only. Okay, so I can connect this capacitance in between gate and ground. So So you have five capacitance now: CL, CGD, CGS, CGD1, CGS1. Apart from this five, another one is CDB1 that will consider the body effect also. You know that in a MOSFET you're having four terminals actually. Even though physically I'm showing three, that is gate, drain and source. Apart from that, you're having a substrate or a body terminal which will be normally connected to source. Okay. But while considering the body effect, what we have to do is we will not be able to connect this body always to the source. So we have to connect this body to ground. So in between the drain and body, there exists another capacitance which is known as CDB1, which should be taken while considering the frequency response. So if a MOSFET is considered to have a body effect, understood what is body effect means? Already this body effect has been discussed in second module. You can go back and refresh, but I'll explain now. Normally in a transistor, this gate and the source and body, it will be tied together, but there are situations when this connection has been detached and the body will be connected to ground rather than connecting to source. So there exists a separate voltage or junction between the drain and body now. Okay. So that drain body capacitance is now represented as CDB1, which you have to consider as an internal capacitance and which should be considered to find out the frequency response effects as well. Okay. So I repeat how we are going to find the frequency response. To find the frequency response, you should consider all the available capacitors of this particular circuit one by one. Individually you have to take each and every capacitance, go through that terminal, look into that open terminals of the capacitance, you will find a resistance, multiply the resistance and capacitance value, that will get the time constant for you. Okay, now similarly you will have six time constants here because you are having six capacitors here, isn't it? So sum together all these time constants to find the final one, and substituting in 1 by 2 pi into the time constant, that is tau h, you will get the frequency, cutoff frequency fh. So that is what we are going to find it now. So first of all we'll be considering the first capacitance, that is cgs1. Okay, so consider the capacitance cgs1. You know what is cgs1? Cgs1 is a capacitance that is available between the gate and source. Since source is at ground, you can connect the cgs to the ground. Now looking into this capacitance, see the only resistance that is observed here is Rsic, isn't it? When you open these terminals and looking into it, the only resistance that you can find is Rsic. So this is your RGS1. RGS1 is nothing but the resistance that is obtained by looking through the open terminals of CGS1. So RGS1 can now be represented as Rsic, which is given by equation number A. So that is with the first case. Now going to the second case, similarly, see you have six capacitance in this figure. So you have to approach with six different cases. Okay. Now going to the second one, that is CGD1. What is CGD1? CGD1 is the capacitance that is connected between the gate and drain of Q1. But unfortunately, see the when comparing with the previous capacitance, this capacitance two terminals, it is being connected at the two terminals like gate 1 and drain 1. Okay, so when you open this, you can't find any resistance directly, unlike the previous case. Okay, when you are opening CGS1, you will be able to find Rsic, but that is not the case with CD1. When you are opening CGD1, you are not able to find any resistance here. Do you find any resistance across these two terminals? There is no physical resistance connected between these two terminals, so I can't find CGD1 with a direct observation. Okay, physically observing across these two terminals, I won't be able to find the resistance that is connected across the capacitance CGD1. So for this we have to perform some analysis. Circuit wise analysis is required to find the open circuit resistance. Understood? That is to find RGD1. What do you mean by RGD1? RGD1 is the resistance that is obtained by looking the open terminals of CGD1. This you have to find out. So for this we'll have to use some signal analysis or circuit analysis. Okay, so for that what I'll do is I'll be putting a dummy voltage across gate 1 and drain 1. Okay, so whatever the capacitance now we have across this gate and drain, we will remove that, and then what you will do is we will be connecting a voltage source across these two terminals. Understood? See, previously we have a CGD1 between G1 and D1. Now what I will do is I will remove the CGD1 Understood? I'll remove the CGD1, and in place of this I'll be putting a dummy voltage which is known as Vx. Why it is called dummy? Because this is just physically, analytically I'm doing, not physically. Okay, just to calculate the equivalent resistance between these two terminals, I'll be putting a dummy voltage source as shown in the diagram here. Okay, so here it is positive, here it is negative, so there will be a current flow which is represented by Ix. Okay, so there is a current flow Ix, and this voltage divided by this current Ix will get you the resistance RGD1. So RGD1 is a resistance that is to be found out across the terminals G1 and D1. Now at D1 you are having RD1. Okay, at the drain 1 you are having a resistance RD1, so that I have shown here. Again, through the transistor drain you are having a current also, that is a drain current. You know the equation for drain current as Gm into Vgs. So as this particular diagram is connected to that first transistor, you will put the parameters with the subscript 1, so Gm1 into Vgs1. And here when you draw a small signal equivalent circuit, in this particular case you will not use any more inputs because this is not a small signal. Okay, so this voltage you have to what, small circuit. Okay, so only left out resistance in that particular terminal is Rsig. So this Rsig will directly connected to ground. So that is the small signal equivalent circuit which is used to find the value of equivalent resistance that is obtained across gate and drain. Okay, I repeat, in between the gate and drain you have a capacitance CGD1. I want to find the equivalent resistance obtained when you look through the CGD1, but unfortunately I am not getting any resistance by direct observation, so we have to go to a circuit analysis. So for that I will be connecting a voltage source between these two terminals, and this voltage source is producing a current flow Ix, and this voltage divided by the current Ix through these terminals will give you the total resistance. So to find this we have to consider the current at the transistor. The current at the transistor can be represented by a dependent current source which is known as Gm into Vgs1, because Vgs1 is going to determine our output current, isn't it? Vgs1 is the input voltage, so that is going to determine the output current. So always the output current of a transistor can be represented by a dependent current source. Okay, it is voltage dependent current source. Because of the voltage the current is varying, so because of this voltage Vgs1 I am getting a different current at different instance of time. So always a drain current can be considered as a dependent current source which is represented by Gm1 into Vgs1. And also at the drain you are having a resistance which is Rd1, which is something internal, so I just represented it as Rd1 as of now. Okay, now our intention is to find RGD1. To find that we have to find the ratio of Vx by Ix. Okay, we have to find the ratio of Vx by Ix to find this RGD1. For that what you will do is you will be applying KCL at node gate 1. So apply KCL at this particular node. So you can see that this current is leaving here. Leaving current is equal to entering current. That is what is known as KCL, isn't it? So this can be also considered as leaving current. So you know that the current is nothing but potential difference divided by resistance. Okay. So what is the potential at this terminal? Since it is ground, it is 0, and this can be considered as VGS1. Okay, this voltage is the voltage at gate 1 is VGS1 because source is at ground. Okay, so the voltage at the gate terminal can be considered as VGS1. So this VGS1 minus 0 divided by Rsig, that is VGS1 by Rsig, plus Ix, this is also leaving. Okay, so plus Ix is equal to 0. Is there is any entering current at this particular node? There is no entering current, isn't it? So both the currents are leaving, so that you can add those two currents equal to 0. So Ix will come to the right hand side, so that will become minus Ix as per this equation number 1. Okay, so any doubt with this particular equation? So this equation you got by simply applying KCL at node number G1. At node 1, at node G1 you are not having any entering current, both the currents are leaving. Ix is also leaving current, and whereas the current through Rsig is also leaving, which you can be represented as Vgs1 by Rsig. Okay, plus Ix is 0. That Ix will come to right side, so that will get you minus Ix. Now coming to the drain part. Okay, the drain part, again apply KCL here. Here you can find that this Ix is entering to drain. This is entering. So Ix is equal to, this one is leaving. Again, this can be considered as leaving. So Ix is equal to Gm1 Vgs1 plus the current through Rd1. What is the current through Rd1? It is this voltage divided by this resistance. What is this voltage? Can you tell me what is this voltage? It is nothing but the voltage at the drain. The voltage at this drain is equal to this input plus this voltage, isn't it? Whatever the voltage at gate plus Vx will get you the total drain voltage. So instead of putting VD1, the voltage at drain 1 can be now represented as the gate source voltage plus Vx. That is what is being mentioned here. Okay. So VGS plus Vx is nothing but the total voltage that is getting developed at the drain terminal divided by the resistance RD1. So that will be the total current through RD1, which is equal to VGS plus Vx divided by RD1. Okay. I repeat again. So at the drain terminal, you are having the entering current Ix. So entering current Ix is equal to leaving current. This is leaving. So Gm1 Vgs1. Again the leaving current through Rd1. To find the leaving current through Rd1, you have to find the voltage at this terminal. This terminal's voltage you have to find out. To find the voltage at the terminal drain 1, what you have to do is you have to add the voltage at this terminal plus the dummy voltage. Okay. What is the voltage at G1? It is equal to VGS1. Okay. So that VGS1 plus Vx will get you the total voltage at the drain terminal. Then that voltage divided by the resistance Rd1, that will get you the total current flow. Okay. So these two are leaving current. This is the only entering current. Now we have to solve these two equations to get the ratio Vx by Ix. Okay. So for that, what I will do is from equation number 1, I will take VGS1 in terms of Ix into Rc. So take this to the other side, cross multiply, you will get VGS1 as minus Ix into Rc, and put this equation in equation number 2, because I don't want to represent VGS1 anymore, because VGS1 should not come into picture, because you have to find the ratio of Vx by Ix, isn't it? To find RGD1, you have to find the ratio of Vx by Ix. So you are not interested in VGS1. So wherever VGS1 you are finding in equation number 2, just replaces it with minus Ix into Rc. So your equation will go like this particular value. Now all the terms having Ix you can take to the left side, and the only term you have with Vx is this thing, Vx by Rd1, which you can keep in the right side. Okay. Now take common here. Take Ix common here and take LCM. What is LCM here? Rd1 will be the LCM. So you have to multiply this Rd1 with these two terms. So inside the bracket you will have Rd1 plus Gm1 Rd1 into Rc plus Rc whole divided by Rd1. That Rd1 and this Rd1 will get cancelled. Okay, here also you are having Rd1. When you take LCM with Rd1, here also you are having Rd1 whole divided by Rd1. These two Rd1s, they will get cancelled each other. Okay, so that is this equation. Now observing this equation, now you can easily find the ratio Vx by Ix. So that will be like this. And here the common factor with the last two terms is Rc, which you can take outside. So when you take Rc outside, in between inside the bracket you are having 1 plus, this is 1, isn't it? When Rc is taken outside, in this place you are having 1 plus, here you are having Gm into Rd, that is Gm1 into Rd1, which is equation number B. So just now we have analyzed two cases. Case A was with respect to which capacitance? With respect to which capacitance? CGS1. Okay, CGS1 was opened, and across I have observed the resistance as RGS1, which is equal to Rc. So Rc is the only resistance that you can find out when looking through CGS1 as per case A. Now case B, what I have done is I have considered CGD1 as a capacitance, but looking into that I can't find any resistance directly, or with an physical observation I won't be able to find the direct resistance. So for that I should perform some circuit wise analysis. For that only I have drawn this small signal equivalent circuit by connecting a dummy voltage source and representing a current across the two terminals by considering Rd1 and Rsig at the two terminals, gate and drain, and this is your drain current. Then applying KCL at the node G1 and D1, solving these two, you got the equation for Vx by Ix. So those ratio of the dummy voltage divided by that current, that will get you the value of RGD1. Okay, now considering the other capacitance, consider the CGD2 and CL, or the CGS2 and CDP1. I think these can be combined together. Why these two capacitance are combining together? Because they are parallel to each other. Okay, see, when will the two capacitance will become parallel to each other? Only if they are sharing the common terminals, isn't it? Only if they are sharing common terminals means you will have a parallel effect. You will get a parallel effect, isn't it? So this CGS2, one of the terminal is connected to gate, and this CDB1, okay, this CDB1, one of the terminal is connected to ground, but this gate is grounded here. Okay, I repeat, the gate of this one of the terminal of CGS2 is connected to gate, which is further at the ground. At the same time, one of the terminals of CDB1 is connected to ground. So these two grounded are common only. These two grounds are common only. Similarly, here one terminal of CGS2 is at the source. Again, this CDB1, one terminal is at D1, but D1 is connected to source 2. Drain of Q1 is connected to source 2, isn't it? So both the terminals of the two capacitors are shorted together, means eventually we can find that the two capacitors are parallelly connected. Okay, so observe the circuit diagram very carefully and identify that this CGS2 and CDB1, the CGS2 and CDB1, they are parallelly connected. So what is the effective capacitance? When you have the two capacitance connected parallel to each other, the total capacitance is nothing but the sum up of individual capacitance, that is CGS2 plus CDB1. Okay, now when you look across these two capacitance, what you can find now? You have to assume the total effect of CDB1 and CGS2 together. I told you the sum effect will be your parallel. I mean, the parallel effect is equivalent to the sum of the individual capacitance. And when you observe this, we can find the resistance as RD1. Okay, when you look into this capacitance, you can find the only resistance that is available is RD1, which is internal resistance of drain 1, isn't it? Any doubts? See, when you look into the CDB1, what is the resistance that you can find out? It is a resistance that is connected across the drain 1, which is something internal to the transistor. And note that the CDB1 is parallel to CGS2. So when you look into the CGS2 also, the only resistance that you can find here is RD1. RD1 is the drain resistance of Q1. So what is the total resistance that you obtained when you combine these two values and looking into the open terminals? The resistance is nothing but RD1. Similarly, you can pair up other two capacitance. Now, till now we have finished with four capacitance, isn't it? CGS1 we have taken, CGD1 also we have taken, again we have taken CGS2 and CDB1 together. Now left out cases are CL and CGD2. Again these two will be parallel. How these two will be parallel? See, one end of CL is at drain. Here one end of CGD2 is also at the drain, isn't it? The other end is at gate 2, but gate 2 is ground. Here the other end is at ground. So these two grounds are common. These two grounds are common. Again, these two terminals are drain 2 only. So obviously CL and CGD2 will be parallel with each other. So again the combination will be CL plus CGD2. Now when you look into the CL, what you can find? When you look into the CL, you don't consider RL, because RL is a physical resistance that is acting as a load. Okay, so don't consider this RL while performing the analysis of frequency response, because RL has no role in determining the frequency response. Okay, so when you look into this RL, the resistance that you can find is nothing but R out. What is R out? R out is the output resistance of Q2. Understood? So CL plus CGD2 will together give you an equivalent resistance which is equal to R out if there is no load. If there is no load. Okay. But if you're connecting a physical load externally, means obviously that is going to be come across parallel with the output resistance. Okay. Then the effective resistance will be R out parallel RL. Okay. Because you may be considering the gain with the load and without load, that is open circuit voltage gain as well as the overall voltage gain, isn't it? That is a gain will vary with respect to frequency. Okay, so while determining the frequency response, normally what you will not consider the load. Okay, but you are, if you are applying the load and then analyzing the frequency response, means this R out will appear parallel with the RL. So that will be the total resistance that is obtained when looking through the combined capacitors CL and CGD2. Now you have four distinct cases A, B, C, and D. Now product the corresponding resistance and capacitance value. So from case A, you have obtained RC as your resistance, and the capacitance was CGS1, isn't it? This was a result of case A. So you have to multiply this CGS1 and RC together. So CGS1 into RC, that is a first time constant. Now coming to the second time constant, case B. What is case B? Here you have obtained this much resistance. So this much resistance multiplied by which resistance, which capacitance? It is CGD1. Okay, CGD1. This is the second time constant. See, first term and second term. Coming to the third term, this entire capacitance multiplied by RD1. This is the third time constant. And the fourth case, the total capacitance CL plus CGD2 multiplied by R parallel RL. So adding all these four terms together, four cases together, you will get the total time constant torch. Now, when you observe the first two cases, you have RC common, isn't it? So there are two terms where RC is common. So you can remove this bracket and take RC common from the first term and this term. So what will be the term, that the resultant term? So when you take RC common from this term, you have CGS1 over here, plus from this term you have CGD1 into 1 plus GM1 into RD1, because the CGD1 you have to take along with this term also. Okay, so CGD1 into 1 plus GM1 into RD1 whole multiplied by RC is outside. Now what about the second term? Here you have having RD1 here. Here also you are having RD1. Again, you can take RD1 outside here. So when you take RD1 outside, what is the pending parameters? Here you have CGD1 plus the remaining thing CDB1 plus CGS2. And coming to the third case, this is the third term which you can directly return. Okay, there is no change for the third term. Now coming to a special case where we are interested in. So this is very important, this particular case, when RC is equal to 0. Okay, we are not going to put any resistance in the input side. Okay, what is the speciality of RC? What is the speciality of RC? RC is something, a resistance which is offering to the input signal. Okay, so if you are putting an RC in the input terminal, if you are putting an RC into the input terminal, there will be some voltage drop across RC. So whatever the voltage you have connected as a signal, from that a particular portion has been dropped across RC, and the remaining voltage will be considered as VI. Okay, so whatever the voltage you have at the input VC, from that a particular amount of voltage will be dropping across RC, and the remaining voltage will be available across CGS1, that is nothing but your VI. But assume that if there is no RSIC, what will happen? If there is no RSIC, means there is no drop. There is no drop across RSIC. So VSIC will be equal to VI. So whatever be the input signal, that will be coming across a transistor input. Okay, the input signal will be equal to the actual input of the transistor terminal, that is VI. But whenever there is an RSIC, then we can't say that VSIC is equal to VI, because some of the voltage will get dropped across RSIC. The remaining voltage will be coming into the transistors input terminals. Now here in as a special case, we are analyzing the frequency response, without RC. So what you have to do is, so in this resultant equation I'll be putting RC as 0. So wherever you find RC, take it as 0. Okay, so this term will vanish, isn't it? This term will go. So only these two terms will stay back. The first term, it will be cancelling because of this setting RC is equal to 0. So I told you that setting a large value of RL will increase the gain of cascode amplifier, isn't it? That is, in the small signal analysis, we have learned two different cases. Whenever this RL is equal to small letter R0, small letter R0 is just the output resistance of the transistor. So whenever you are trying to maintain the load resistance equal to just the output resistance of a transistor, then this cascode amplifier has got no use, because it is providing only small gain which is equal to A0, that can be provided by a typical common source amplifier. So no need to cascode these two together as we have learned in the last class. But when you can provide a load resistance RL equal to A0 times of R0, A0 is the intrinsic gain of a transistor. Okay, so A0 into R0, that much load if you can fix means you are going to get an appreciable gain with this cascode amplifier. At that situation only you are completely exploiting the benefit of the cascode amplifier. So what you have to do is you will be using a very large value of R. So what you have to do is in equation number 5 consider that the load resistance RL is very large. What will happen if load resistance value is very much large means this term will get vanish because this is going to be dominant, isn't it? So the third term of equation number 5 is going to be dominant if we are considering a very high value of RL. But if you are not considering the value of RL means what will happen? This is going to be neglected. Okay. So here we are assuming two distinct parameters. One is R sig is equal to 0 means you are not connecting any resistance at the input side. Secondly, you are maintaining a very high value of load resistance that will keep the third term of equation number 5 there itself. At the same time, the first term of equation number 5 will get vanished because that is comparatively smaller. Okay, so earlier we had 4 different cases. From that I had simplified that equation by taking the common terms, and I had only 3 terms. Then I assumed that R sig equal to 0. Then I neglected first term. Then I assumed that RL is very large, so that I assumed the second term also. So the only term that is left out with us is now third term. So this is the total time constant. Now simply by putting in this equation you will be getting FH. So the cutoff frequency FH is now being dominated by the value of load resistance RL, since you are taking a very large value of RL. Okay, and R out, you know, R out is just the output resistance of second transistor, which is equal to A0 into R01. This we have learned in the previous class. That is how output resistance of the cascode. In the small signal analysis we have derived this. Okay, the cascode amplifier is able to get an output resistance R out which is equal to A0 times the resistance of previous stage. Previous stage means common source. The first stage you are having common source. Second stage you are having common gate. So the common source is having R01. Understood? The common source is having an output resistance of R01 that will get multiplied by A0. So there is a very large value of output resistance. This is the total output resistance of the entire cascode. R01 is the output resistance of only one stage, whereas R out is the output resistance of the entire amplification stage. Okay, so just by substituting you will get the value of FH. So here I have just represented these two parallel effect as RL dash. Just I have represented it as RL dash, that's all. Okay, so A0 into RL dash. So this is the conclusion. See, this is the equation for cutoff frequency FH of a CS amplifier, what you have learned in the previous module. Okay, in the third module we have derived the equation for FH, cutoff frequency of a typical CS amplifier. Now this is the cutoff frequency FH of a cascode amplifier, what we have derived as of now. Compare these two. What is your inference? Which cutoff frequency is larger and which is small? Which is larger and which is small? See, here A0 is coming in the denominator, means FH is small for cascode. Okay, so for cascode amplifier, your cutoff frequency has been decreased by a factor of A0. Okay, so your bandwidth has been decreased. Since FH has been decreased, assume in the x-axis your FH will come closer to 0. Okay, this was the FH for CS. See this graph. See this graph. This is the cutoff frequency of a common source amplifier. But when we cascoded this common source with the common gate, it became a cascode amplifier. But the result is that your cutoff frequency has been decreased by how much times? A0 times, because A0 is in the denominator, isn't it? So that much bandwidth you have decreased. Means your cascode amplifier will not work beyond this FH. Means beyond this FH, your gain is, see, your gain has been decreasing beyond this cutoff frequency. This is not appreciable to cascode, but the benefit is that you are achieving this much increase in gain. Okay, with an ordinary CS amplifier With an I repeat, with an ordinary CS amplifier, you are having this gain only GM into RL dash. But now see, your gain has multiplied by A naught because you are having two stages, isn't it? So the overall gain now has become A naught times of GM into RL dash, where the gain has been significantly increased by A naught times. Okay, but your bandwidth has gone decreasing. It has decreased to a factor of A0. Okay, so means whatever gain you are trying to increase, perhaps you are trying to increase 3 times gain, means your bandwidth will become 1 by 3rd. Perhaps you are trying to increase 4 times gain, means your bandwidth will get 1 by 4th. Okay, means your gain bandwidth product is going to be a constant. Understood? So this is a very important question. Justify that the product of gain and bandwidth. See this particular statement. The product of the gain and bandwidth of a sorry, cascode amplifier always remains constant. So that you have to justify by this particular derivation and this particular graph. Okay. But the case is, you have to realize the case. What is the case? Case is R sig is equal to 0. Isn't it? You are not using any R sig. Remember the approximation what we have done in the earlier page. Normally you had three different terms, but only by setting R sig only you had reached in this particular equation. R sig equal to 0 you have assumed. Only then only you have written this equation number 6 and then I found FH value. So you got this FH value only after setting R sig is equal to 0. So that case you have to keep in mind. So this particular result is validated only for R sig equal to 0 case. Okay. For non-zero R sig value, you will not find this particular response. Understood? So I repeat, when you are trying to increase the gain of an amplifier by cascoding it, definitely you are going to increase the gain by A naught times. But there also, you have to maintain your load resistance value. Okay. If you are able to maintain your load resistance value approximately equal to A0 times of R0, then only you will be able to enhance your gain. Otherwise, your gain will be just same as set of CS. That condition also you have to remember. Anyway, by setting all those proper conditions, you are able to increase your gain this much. But you are compensating on bandwidth. Your bandwidth you are sacrificing. How much deterioration in your bandwidth you have observed? A0 times your bandwidth has been decreased. So when you multiply this increment in gain and decrement in bandwidth, do you find any change in the product? Suppose 2 times you have increased, half times your bandwidth. So 2 into half is 1. So there is no change in gain bandwidth product, isn't it? So the product of the gain and bandwidth of a cascode amplifier remains constant if only if R sig equal to 0. That you have to keep in mind. Only if R sig equal to 0, this particular statement is validated. Otherwise, it doesn't happen. See, when R sig equal to 0. Understood? So this is very important. This particular case is very important. Now going to the next topic, cascode current source. So till now we have discussed two topics. One is the small signal analysis and second one is frequency response. Now going to the current source. You know what is current source? Current source is used to produce a definite amount of current in any desired location of an IC, because all these are fabricating inside an IC. IC will have numerous discrete components. Each and every components will have different current. It requires different current value. So you will be able to design a particular current source at one particular location, and by using some mirror circuits you will be steering this current from that location to all other part of the ICs. So at some part of the ICs you require some source. Source means something which generate a current. Okay. So once you generate a current at a particular point, from that point you can steer the current to all other locations by using mirror circuit. So that is the use of mirror. So mirror is used to steer the current from one point to another point. So here we are looking how to design a current source by using cascode configuration. So this is basically the circuit diagram of a cascode current source. As the name indicates, here also we will be using two different configurations, that is common source and common gate. See, this is your common source. Which is this configuration? which is this configuration. Here the base gate is common, input is to source, output is taken from drain. Input is at the source, output is taken from the drain. So this is CG. Okay, the lower part of the circuit is CG, whereas the upper part you are taking the output from drain. This is drain, this is gate, this is source. So this is common source. Okay, so common source, because your input is at V bias 1. This is your input. This is your output. Drain is the output. Okay, this is your supply. So this is a common source. Source is common for both the input as well as the output. So this CS stage and CG stage together it forms a current source. So this particular circuit is producing a current I. The value of this current I depending on the biasing conditions. You know that every current source will produce a required amount of current only if the two transistors work in saturation region. Okay. Whatever the kind of transistors that you are using, whatever the kind of MOSFETs that you are using to produce a current, you will have to maintain those transistors in saturation region. For that, you have to apply suitable biasing voltages. So that biasing voltages you have to ensure to get a proper current I. And note down the output resistance of these two. This is R01. Being this is a common source configuration, you have the output resistance as R01, and you know the speciality of common gate. What will this common gate will do is, common gate will increase the output resistance by A0 times, that is A0 into R01. What is A0? A0 is the gain of which transistor? A0 is a gain of Q2. Okay, Q2 is acting as common gate, so this is A0 multiplied by R01. Okay, so A0 is nothing but GM2 into R02. That is the intrinsic gain of second transistor. GM2 into R02 multiplied by R01. This is the overall output resistance. So the speciality of this configuration is you will be able to get a large output resistance. You know what is the speciality of getting large output resistance? Because that will affect your load. Because the overall RL dash, it is RL parallel RL, isn't it? So you should be able to get a large output resistance so as to increase high gain of a cascode amplifier. Remember, no? You will be able to exploit the benefit of the cascode amplifier only if you are getting a large load resistance. Okay, if you are able to fix a very large load resistance of the order of A0 into R0, then you will get an amplified output. Okay, otherwise it is same as that of the gain of CS, which doesn't make any use. Okay, so keep it in mind that the cascode amplifier will act as a beneficial one only if the output resistance is enhanced. That output resistance can be enhanced if you combine these two configurations in this particular way. How it is being enhanced? It will enhance the output resistance A0 into R01, where R01 is the output resistance of typical common source. A0 is the GM into RD or GM into R0 value, which is the gain of the second transistor, that is common gate. Okay. So this much output resistance you are getting. So that much output resistance is able to deliver by a constant current source so that your amplifier will amplify it with a very much higher gain. Okay. Now another configuration of cascoding is double cascoding. So whatever we have discussed now, that is in heading number C, that is a typical MOS current mirror, sorry, current source. Okay, it is a current source circuit using a cascode configuration. Now again we are using another current source where you will be using three transistors. So this configuration is known as double cascoding. So additionally I have stacked one more transistor beyond Q2. So earlier it was Q1 and Q2. Now I am trying to stack one more, that is Q3. Okay. So again, I just reverse the order of connection. See, this is your common source now. This is your common source. Understood? Q1 is a common source and this is common gate and this is also common gate. So you are having two common gate as of now and one common source. And you know what is the output of common source resistance is R01, and what the common gate will do is common gate will enhance the output resistance by A0 times, which is nothing but GM2 R02 into R01. But here I have used one more common gate which is stacked over the previous Q2, so this it will be able to enhance the output resistance by A0 again, that is GM3 into R03. So the overall output resistance will now become GM3 R03 into GM2 R02 into the resistance R01. Suppose all the three resistances are same, because all the three transistors are matched transistors, means of course your output resistance are going to be same. That is R03 equal to R02 equal to R01, isn't it? And consider that the product becomes R0. So GM3 into R03. What is GM3 into R03? It is A0. Again GM2 into R02, it will be also A0 because R03 is going to be same as R02. Similarly, GM3 same as set of GM2. Okay, so both the transistors, they are having same transconductance. Both the transistors, they are having same output resistance. So normally their intrinsic gain is going to be same. So this is A0, this is A0. So A0 into A0 is A0 square into R0. So when you consider the previous case and present case, the difference is here you are having only the output resistance which is equal to A0 into R0, but here you are having A0 square into R0. So that is a benefit of double cascoding. So double cascoding is able to provide a output resistance of A0 times as that of the typical cascode current source. So a typical cascode current source is able to produce only A0 into R0, whereas double cascoding, that is stacking one more common gate configuration, is able to provide an output resistance of A0 square into R0, where you are getting a large output resistance of A0 times. Understood? And try to keep it in mind that benefit of increased output resistance is increase in gain. Only if you can achieve a better R out value, that will yield a better gain. Otherwise, there is no use of current cascode amplifier. Okay. So while designing a cascode amplifier, you require a current source. That current source is what is shown here. Understood? So let me take the first circuit diagram what you have studied in this particular module. See, this is the actual circuit diagram of a cascode amplifier here. Here you have used capital I. This I can be generated by the circuit diagram what I have shown now. Understood the relation? This is the amplifier circuit, but this amplifier circuit will operate with the help of the bias current source. That current source is now mentioned in this MOS cascode circuit. This thing. Okay. So this circuit is used to produce that capital I. But the thing is that the circuit is able to produce an output resistance of A0 into R0, which you will get as an enhanced version of double cascoding. Okay, double cascoding that will be enhanced by A0 types. This is another version of current source, that is double cascoding. Any doubts? But the drawback is that the hardware complexity increases. Okay, so double cascoding amplifier is increasing the output resistance and still you can increase the gain. But the thing is that you are able to use more hardware, that is more stacking of transistors under one power supply. So under one power supply you are using more transistors, that will yield better power consumption also, I mean better power dissipation also. So the entire IC will get heated up very quickly because of the use of much more hardware under one power supply, because you are using only one power supply VDD. Under this power supply rail you are using three transistors together, so that will yield more power dissipation and your transistor will get heated up in a much fast manner. Okay, to avoid that, what you will do is you will use a folded cascode. So this is the third configuration of cascode. One is the typical cascode current source. Secondly, to increase the output resistance, I have double cascoded it. Again, the problem with the double cascoded is excessive power dissipation and heat dissipation because of using three transistors under one power supply. Here I have just used two transistors, so I have consumed the hardware, I have used less hardware, and at the same time I'm not using this particular circuit under VDD. Okay, so this power supply is meant for Q1, whereas Q2 has not been connected directly in series or in series with Q1 with respect to VDD. So by connecting in this particular manner, you will be able to achieve the same output resistance what we have discussed in the first case, that is A0 into R0. At the same time, better Q point and better power saving can be done. Okay, and the difference is that here you are using PMOS instead of NMOS. So not identical. So this is NMOS, but this is PMOS. Only by connecting PMOS in this manner, you will be able to get the same output resistance what we have derived in the first case. That is the typical MOS mirror. In the MOS mirror, you have derived the output equation, output resistance equation as A0 into R0, isn't it? So that A0 into R0 output resistance can be achieved with this folded cascode also. But the thing is that you have to get another transistor which is PMOS, and PMOS is under I2 and NMOS is under I1 because these are two distinct circuits. You can't bias the two transistors with the same current source. Okay, so this is an amplifier circuit. Again, this is a cascode. But the thing is, you are using two different current sources, I1 and I2, separately for Q1 and Q2 because Q1 is NMOS and Q2 is PMOS. So that is a drawback of the circuit. But the problem of excessive participation, better Q point can be achieved here. Okay, problem of heat dissipation, power dissipation can be avoided by using the folded cascode configuration. So let me conclude the classes, what we have learned now. So first we have done the small signal analysis where you have derived the expressions for input out resistance, output resistance, then output voltage gain, open circuit voltage gain, overall voltage gain, everything we have done. And we discussed about the benefit of cascoding, but the benefit of the cascoding can be only exploited if we set the load resistance in an appropriate manner. That we have concluded in first one. Second topic, we have derived the equation for the cutoff frequency FH by considering 6 capacitance individually. But there also we have one approximation, that is Rsig is equal to 0. By setting Rsig equal to 0, we found that the cutoff frequency of a cascode amplifier will come down by A0 times. So gain is increasing by A0, cutoff frequency is coming downwards, means your bandwidth is going to decrease. So gain bandwidth, the product of a cascode amplifier, remains constant provided there is a condition is Rsig is equal to 0. That is the conclusion of second heading. In the third heading, we have discussed about the typical cascode current source. That is how that current source is able to produce a large output resistance, that is A0 into R0 times. Again, we discuss about the benefit of double cascoding. That is, normal cascode amplifier is increasing the gain by A0 times, but the double cascoding will increase the gain by A0 square times. Okay, but the thing is that you will require one more transistor to be stacked, so that will increase the power dissipation and heat dissipation, so that will burn your IC. Next one we have come up with the folded cascode where we are able to decrement the use of one transistor. So there we are using only two transistors, but we can achieve the same gain as that of the cascode amplifier. Okay, but the thing is that we are replacing NMOS with the PMOS. So we are using two different transistors. Using two different transistors means you require two current source I1 and I2 separately. That is a drawback of this amplifier. Okay, when you see the circuit diagram of a typical cascode amplifier, you are using only one because both these transistors are NMOS. But in the folded cascode, you are using PMOS other than NMOS. So there we require I1 and I2, that is two distinct current source. That is a drawback of folded cascode. Okay, so all thing you have to require is just to draw the circuit diagram, its explanation and the benefits and drawbacks of the three configurations, that is current source, double cascoding, folded cascoding. Okay, and the next class we will be discussing the advantages and features of BiCMOS, and then we will look into the different mirror circuits. Okay, hope you have understood the logics and concepts. Any doubts you can ask now. Any doubts, please ask.
Details that summarize
Okay, then thank you.
Start